Good evening. Today is our fifth lecture, and in the previous lecture we already started our discussion on the governing equations, and in specific we talked about the continuity equation. Okay, today we will continue this discussion, and if you recall from the previous lecture, then yeah, so we were at this point. So basically, if you see the equation del by del t rho n alpha n plus del by del xi rho n j n I equal to I n represents over here nothing but the individual phase continuity equation. Okay, so if I have to name this equation, then I will be naming this equation as individual phase continuity equation. Okay, because I told you that if I have two phases present in a system, then I will be writing this equation separately for liquid and gas. If I have say multiple components present in a system, then my n will be equal to a b c d. So I have to individually write this equation for each and every component. Okay, and in this equation, one distinction from the single phase continuity equation is that here this In can be positive or it can be negative, whereas this In represents nothing but the mass interaction term. Okay, and typically interactions we can see either interactions can be in terms of phase change or interactions can be because of the chemical reactions. If say chemical reactions are happening, then also what will be happening? One type of reactant will lose its mass and it will be getting converted to some product, and product will keep on increasing its mass. Okay, so that's why this particular equation we call as nothing but the individual phase continuity equation. The meaning is, if I take any component, then I have to separately write this equation for each and every component present in the system. Okay, now this interaction term In, if I simply consider two phases, one is dispersed phase, another is continuous phase. Say, if this term is positive for dispersed phase, the meaning is this mass of the dispersed phase is actually increasing within the control volume. Okay, then in that case, this term will be nothing but of equal magnitude and negative for the other phase, because if in a system of two phases, if one phase is losing mass, is gaining mass, then obviously the other phase should have gained the mass by the same amount. Is this point clear? You can take a simple example. Say if you have a closed chamber, this is your control volume, and in that closed chamber some part is filled with liquid and some part is vapor. If your new vapor bubble is actually appearing, okay, so that is nothing but a gain of mass in the vapor phase. So of course that vapor bubble, from where it is coming? It is nothing but coming from the surrounding liquid phase. So that's why that particular liquid phase will be losing the mass. So in that sense, I can say that if I take the sum of all interaction terms for n phases, then that sum should be equal to 0. Is this point clear? All are clear with this idea? So sum of the mass interaction terms has to be nothing but equal to 0. Now, what I can do, this is my individual phase continuity equation. If I take all the individual phase continuity equations and if I take their sum, okay, if I take their sum, then ultimately what I will be getting? I will be getting a summation over the phases. Is this one clear? Because this equation separately I can write for n equal to a, n equal to b, n equal to c, d, etc. If I do sum of all these equations, then I will be having the first term as del by del t of rho a alpha a plus rho b alpha b plus so on up to like this, and then second term I will be having del by del xi into rho a JAI plus rho B JBI plus so on up to like this, and in the right hand side I will be having nothing but INA plus INB plus so on up to like this. Okay, so now this term I can write simply as nothing but summation over the n rho n into alpha n, and this I can write summation rho n into JNI equal to 0, because in the right hand side summation of all interaction terms will become equal to 0. So this particular equation now does not account for any individual phase, rather it includes all the phases into a single equation. So this is called as combined phase continuity equation. Is this one clear? The way we are writing individual phase continuity equation, if we take sum of all the individual phase continuity equations, then ultimately what we will get is nothing but the combined phase continuity equation. Okay. Now, what we will do, we will try to do some substitutions. So, if you recall, what is summation rho n into alpha n? This is nothing but sum of densities of individual phases into their volume fraction. So, sum of rho n into alpha n is nothing but equal to mixture density rho. Is this point clear? Do you recall this relation? This we studied in lecture number 3. Okay. So, sum of all the densities multiplied by their volume fraction is nothing but equal to mixture density rho, and this particular term JNI, which is equal to superficial velocity, it can also be written as alpha n times UNI, where U is nothing but the local velocity of that particular phase. Okay. So, this also we have studied earlier. So, now I will be doing these two replacements in this combined phase continuity equation, and I can write this as del rho by del t plus del by del xi, and in place of this JNI I have written alpha n into UNI. So, this is now my combined phase continuity equation, but it is including now the local velocity UNI. Is this one clear? Now, here we will be making one assumption. If I say my all UNI equal to UI, what is the meaning of this? All phases are having the same velocity. Okay. So, if all phases are having same velocity, it means in between all the phases their drift velocity is equal to 0. So, no relative motion between the phases. Okay. So, if there is no relative motion between the phases UNI equal to UI, then this term I can take out of the summation sign, because this is same for all phases, and in the summation sign I will be only having the rho n into alpha n. Okay. And rho n into alpha n will become, summation of rho n into alpha n will become nothing but rho, mixture density. So, that is why this term summation, this I can write as mixture density rho, and UNI I can simply replace with UI. So, then I will be getting this equation, and this equation is nothing but my mixture continuity equation. All are clear with this idea? Okay. So, all the different phases can have different velocities, but now we are taking assumption that all the phases are at the same velocity. It means there is no relative motion between the phases. So, in that scenario, this UNI I can take a constant out of the summation sign. So, within the summation sign, whatever term is there, that is nothing but my mixture density. So, now this complete term is only involving the mixture property rho and other mixture properties, mixture velocity in ith direction, that is UI. So, that is why I can call this as mixture continuity equation. Okay. So, later on, whenever we will be particularly talking about the flow through pipes, in particular the bubbly flow through pipes, then we have to estimate that how much pressure drop is happening in the pipe if two-phase mixture is flowing. Okay, so there we will be doing the analytical solution by considering the homogeneous flow model. So homogeneous flow model is actually based on this assumption only. Homogeneous model is applied for the situations where there is no relative motion between the phases. So that's why when I will be using the homogeneous flow model at that particular point, then there we will be using this mixture continuity equation. Okay, is this point clear? So you can write with this equation that this will be later used when we will be particularly talking about the homogeneous flow model. Okay. Okay, now comes further simplification of this equation. So now, whenever we particularly talk about the multi-phase flow problems, of course, the analytical solutions of the multi-phase flow problems is actually quite challenging. Okay, if we account for the variations in all the directions. So that's why majority of the times, one simple assumption we consider that we will talk about only the 1D solution or 1D flow consideration. Okay. So what happens in one-dimensional flow assumption, we consider that if this is a pipe, in this pipe I am not interested in variation of property along the cross section of the pipe. Rather, I am only interested in variation of the property along the length of the pipe. So say this is my length. So at each and every cross section, say this is my cross section 1, A1, this is some other cross section A2. Likewise, I can have infinite number of cross sections. So at this cross section also I am referring to the single property UA1, rho A1. Here also I am referring to some single velocity UA2 and rho A2. So ultimately what I am considering at each and every cross section, I am considering a single uniform representative value, and that value is only moving along the length of the pipe. Okay, so if this type of one-dimensional flow simplification we are introducing, it means we are introducing nothing but averaging over the area. Okay, so if this type of area averaging we introduce, then ultimately the first term of continuity equation we are writing as it is, del by del t rho n into alpha n. But what we have done in the second term, if you see, first thing I have done is I have removed the subscript I from here. Why I have removed subscript I? Because whenever I was considering the generic case, then I was considering all the directions x1, x2 and x3. Now, whenever I am doing the area averaging thing, I am only considering a single direction along the length of the pipe. Okay, and that particular direction I have described over here as x. So that's why I am removing this subscript. Okay, so it is a single direction now, del by del x, a single term. Along with this, rho n, alpha n and un is remaining as it is, but what I have done, I have multiplied this thing with cross-sectional area and also I have divided with area, so that I can account for the area averaging thing into my consideration. Is this point clear? And on the right hand side, this is equal to nothing but I. Interaction term is as it is. So in the second term, what I have done, I have multiplied with area and I have divided with area. Now, if I consider that my pipe cross section is something like this. So in this case, what is happening? This area is nothing but function of x. Area is not constant. So if area is not constant, I cannot take this out. But if area is constant, then this simply area can be taken outside, and then this equation will be simply del by del x of rho n alpha n into. Okay. But if area is variable, then I cannot take the area outside integration. So in this scenario, you can see this is my individual phase area averaged continuity equation. Okay, so this is nothing but individual phase area averaged continuity equation. If I take the sum of all these individual phase area averaged equations, then what I will be getting? Summation of all this. So in case of first term, summation will simply result in mixture density rho plus 1 by a del by del x of area is coming out, and inside I have written summation of rho n alpha n into un, because area A is not phase dependent. In that particular cross section, whatever number of phases are present, actually we are trying to account for their average property. So that's why area I am writing out of the summation sign whenever I am doing summation over the number of phases. Is this point clear? So now this is in the similar way we have written the equation, okay, and further, so here you can see there is one typo. This should be capital N, because we are using capital N for a phase, so this should be capital N here as well, okay. And ultimately, once again, so what is this? This is now combined area averaged continuity equation, okay, and these equations are nothing but applicable only for 1D flow conditions, where we are considering the area averaged conditions, okay. Now again, if I introduce the condition that un is equal to u, so if un is equal to u, then u will be also coming out of the integration, so a into u multiplied by rho n into alpha n, which will become nothing but mixture density rho, okay. So now this is, and particularly on the right hand side, already the summation of in is actually given over here as 0. So this has become mixture area averaged continuity equation, okay, and this is area averaged. Yes, we are taking only in one direction, okay. So this is complete derivative, because we are only talking about the area average thing, so in a simple operation. Because whenever you are using the averaging of area, you are not interested in distribution of individual phases in a area averaged quantity, okay. So within this area, in whatever arrangement phases are arranged, you have to do summation over the phases, not summation over the area. Is this point clear?
Not the function of x.
Sorry?
Not the function.
Area is function of x, but area is not the function of phases. Is this point clear? So there are two things. Whenever we are doing area averaging, you can say that area averaging based on the pipe area or area averaging based on the individual phase area. Of course, defining individual phase area will be very, very challenging. So that's why we are doing averaging only based on the basis of the pipe area. So when we are doing averaging based on the pipe area, in that nowhere the inclusion of actually individual phase summations is coming. Okay, is this point clear?
Means that this is cross-sectional area.
Cross-sectional area of the pipe. Okay. Okay, then comes another description of the equation. So here what is done, this is nothing but again the individual phase continuity equation, okay. Why we are writing this? Because now we want to write this equation in the number density form. So that's why I have again given this definition over here. So if you go further and if you write dispersed phase number continuity equation, what is the meaning of number continuity? So till now, whenever we are writing the continuity equation, we are considering only the volume fraction of the dispersed phase, okay, as identity. Now we will be considering the number of particles present in the system as the identity. So that's why I am calling this as dispersed phase number continuity equation. Is this point clear? The meaning is, say this is my volume, total volume, and in this total volume if I am having number of particles present, okay. So these particles are nothing but dispersed phase particles, and in the surrounding what I am having? Continuous phase, okay. So typically I can make an assumption that in this entire volume ND number of dispersed phase particles are present. Okay. So what I am saying, I am having at any instant within this volume, I am having ND number of dispersed phase particles present. Okay. Now what I want to do, I am considering this. So this type of equation will be applicable, say, for your solid particle kind of thing. So there, or even this can be applied for bubble as well, if we particularly talk about the population balance method. Okay. So later on you will be finding that whenever we are having a complex system having number of bubbles present in that, then we can analyze that particular system using a method called as population balance method. Okay. So what population balance method will be doing? It will be first keeping the initial track of the number and volume of bubbles present, and then using some mathematical models, it will be leading to breakup and formation of a single bubble into multiple, or formation of coalescence of a number of bubbles into a single bubble. Okay. So in that scenario, I have to track two things. One is number and second one is volume. Okay. So that type of method is called as population balance method. So whenever you are using population balance method kind of thing, in that case, of course, the continuity equation, whenever you will be using, you will try to keep a track of the number of bubbles present in the system or number of particles present in the system. So over here what I am saying, say, in this particular system I am having ND number of dispersed phase particles present. Okay. So these dispersed phase particles can change within the system. So that's why del by del T ND. This is the time rate of change of number of dispersed phase particles per unit volume within the system. This, let me write, these are nothing but per unit total volume of the control volume. Okay. Now, these particles, because of the velocity, these can move out across the boundary of this system. So say some particle can come in, say this is a fresh particle entering, and these are the particles which are going out. Okay. So to account for the motion in and out of the control volume, I have to consider another term, so which is the advection term over here. Is this one clear? So this is the advection term which is representing that with the velocity of the dispersed phase, how many number of particles are actually crossing the boundary of the system. Is this one clear? So in a system, if you say you are having 100 particles present and say 5 particles are going out and 3 are entering, so we have to find how much net number is actually interacting through the boundary. So net number interacting through the boundary is actually written using this term. Okay, and this is the net number which is changing within the control volume with time. Okay, with time, how it can change, there can be formation or there can be collapse of few particles. Is this point clear? So that's why you can see that this is my number continuity equation for a dispersed phase. Now, one interesting fact. If I have to define alpha D is what? Volume fraction of the dispersed phase. Volume fraction of the dispersed phase will be nothing but volume of the dispersed phase. So volume of dispersed phase will be number of particles of dispersed phase present in the system into volume of the individual phase. So volume of the individual phase is Vd. And when I have considered this number Nd, then already I have included per unit total volume of the control volume. So that's why this term will give me alpha D. Is this point clear? What is alpha D? Alpha D is nothing but volume fraction. The definition of volume fraction is volume of dispersed phase divided by total volume of the control volume. Okay. Volume of dispersed phase Vd will be nothing but number of dispersed phase particles. These are per unit volume is Nd. So in total V volume it will be Nd into V, and then volume of the individual particle. What is volume of individual particle? Vd. So that is my total volume of dispersed phase, and if I have to find volume fraction, then it will be Vd by V. So Vv will be cancelling out and alpha d will be nothing but Nd into. Is this point clear? So now if I substitute this definition of alpha d in my previous original continuity equation, then what I will be getting? In the original continuity equation, in place of alpha d, I have written Nd into Vd. Is this point clear? So you have to recall the original continuity equation. So del by del T of Nd rho d into Vd plus del by del xi of, in the original equation, rho d into alpha d into Vd was there. Sorry, alpha d into Udi was there. So now along with this, in place of alpha d, I can get Nd into. Okay. So now this is the continuity equation in terms of numbers of particles present in the system. Numbers of dispersed phase particles present in the system. And of course, this equation is nothing but applicable only for dispersed phase. Is this point clear? Now a little bit of manipulation. So what I can do over here, this rho d into Vd I can consider one variable V, and Nd I can consider one variable U. Similarly here, rho d into Vd is V, and this whole is U. And if I now apply the separation of variables rule, so ultimately what I will be getting? One equation I will be getting in terms of derivative of Nd, and other equation I will be getting in terms of derivative of rho d into Vd. Is this point clear? So that is what is done over here. So you can see one equation is where Nd is common outside, and you have rho d Vd by del T plus Udi into del by del xi of rho d into Vd. Is this point clear? And along with this, there will be one additional term, and that additional term from this number continuity equation can be written as 0. Is this point clear? If you apply over here method of separation of variables, then this will be first term, and along with this first term I will be having plus this as my second term. Okay, and this second term from the number conservation can be substituted equal to 0. Then I will be getting this first term equal to Id, and from here my Id is nothing but Nd times, what is this term? This is temporal derivative plus velocity times spatial derivative. So this is nothing but the definition of the total derivative. Total derivative d by dt. You should know basic fluid mechanics and basic mathematics, then only you will be able to understand. So what is d by dt? Del by del t plus v dot del. Is this point clear? Where what is del? Del by del x I cap plus del by del y plus del by del z k cap. Or in tensor notation, how it can be written? Del by del xi. So that is what. So you can see now this udi means velocity of the dispersed phase. So this is this v vector dot this del by del xi is representing the del vector of rho d ud, and this is del by del t of rho d ut. So this will become total derivative or substantial derivative or Lagrangian derivative. So you can call any name. Okay, either this is total derivative or substantial derivative or Lagrangian derivative. Okay. So here one interesting fact is, it is telling you if you simply take this ND to other side, then you will be finding IT by ND equal to dt by ddt. So whenever subscript d is used, it means we are talking about the substantial derivative of the dispersed phase. Why we are writing this d also with this? Because in the definition of the substantial derivative, one velocity vector is also used. Okay, when we are using this dd, then we are referring to that velocity vector of only dispersed phase. Point is clear? So each and every term, whatever we are writing, is having strong physical meaning. So you should be able to understand. Okay? Because every equation is having some physical interpretation. I could have used simple definition d by dt, but d by dt will involve some velocity vector. Okay? But here our velocity vector is specifically targeted towards a dispersed phase. That's why I am writing this definition as dt by ddt, where this subscript d is actually referring to the dispersed phase. Is this point clear? So now from here you can simply see that id by nd is nothing but equal to dt by ddt of rho dvd. What is rho dvd? Rho dvd is nothing but mass of the dispersed phase. So you can see that the mass interaction term per unit number of particles of the dispersed phase is nothing but equal to the Lagrangian derivative of the mass of individual particle. So that is the physical. Okay. So mass interaction of a single phase, mass interaction of a dispersed phase per unit the number of particles of dispersed phase present in unit control volume is nothing but equal to Lagrangian derivative, which simply represents the total rate of change of mass of the dispersed phase within the control volume. Okay, so total rate of mass change means it is including the mass change within the control volume, that is this term, temporal term, which accounts for rate of mass change within the control volume, and second term is rate of mass change across the boundaries of the control volume. All are clear with this idea? So from here I can determine my dispersed phase term like this. Okay.
Why we can't use this for continuous phase?
Because continuous phase, you cannot define exact number present. Continuous phase is nothing but infinitely present. So here everywhere what you have? Continuous phase. Can you isolate continuous phase like this? Small bubbles? So you cannot define exact finite number. Okay, it will be nothing but infinite number. Now comes little bit mathematical manipulation. So here you have to simply understand the numbers and based on that you can do. So if I define eta as nothing but number of dispersed phase particles per unit liquid volume. So this is nothing but per unit liquid volume. So now in total control volume, there can be two phases, as I told you, one is continuous, one is dispersed. So of course, if I talk about the population of air bubbles present in a total control volume, then air bubbles will be present in some surrounding liquid continuous phase. So now I am referring to that situation. Instead of mentioning the bubbles in terms of the total size, I am referring it with reference to the liquid volume. Okay. So in this scenario, what will be total mass of dispersed phase or total volume of dispersed phase? So in terms of this, I can write eta into volume of the liquid, and in terms of my previous definition, I can write eta d into total volume of the control volume. Is this point clear? Eta is number on per unit liquid mass present, liquid volume present, and eta d is number per unit total volume. Okay, so in my total volume Vt, if VL amount of liquid is present, then dispersed phase using definition eta I can write as eta times VL, and same dispersed phase volume I can also write as in terms of eta d into Vt. Is this point clear? Then from here my eta will become eta d into Vt divided by VL. What is VL by Vt? So if I only consider the two component system where one is dispersed phase and other one is continuous phase, I can define alpha d is nothing but equal to by single symbol alpha, which will be equal to volume of dispersed phase by total volume, and alpha L, which will be simply equal to 1 minus alpha. Okay, alpha of liquid or continuous phase is equal to 1 minus alpha if only two components are present. So that this point and this will be equal to nothing but volume of liquid by total volume. So Vt by VL I can write as eta equal to eta d divided by 1 minus alpha. So this is the derivation for this first portion. All are clear with this point? So instead of the per unit total volume, if I use per unit liquid volume, okay, then eta and eta d can be correlated using this definition. Okay, all are clear with this idea? Now go to the second relation. So from this first relation only second can also be estimated. So eta minus eta alpha will be equal to eta d. Is this point clear? And if you say that if V is volume of each particle, each dispersed phase particle. So if you consider that all the dispersed phase particles are of same volume V, okay, in that case you can do some mathematical manipulations to replace this alpha. How you can replace this alpha then? Nd into V. Okay, because V is volume of each phase particle and Nd is number of dispersed phase volumes in the total. Okay, so that's why this Nd into V will be acting as the replacement for alpha, and then if you simplify this equation you will be getting Nd equal to eta by 1 plus eta times V. All are clear with this idea? Then simply if you do further manipulations you can also write alpha equal to eta into V by 1 plus eta V. So these three forms can be simply obtained from the algebraic manipulations between the eta and eta d, considering V as volume of each dispersed phase particle. All are clear with this idea? So you can carry out these algebraic manipulations. So first main important relation I have shown you, and other two you can actually elaborately calculate. Fine. Okay, using these definitions now, if we move further, then what I can do, in the previous equation, this is the equation, okay. In this equation what I can do, I can write it like this: del u d by del x I equal to eta by 1 plus eta v into dd by ddt of volume of each individual particle. So how it is coming, let me show you. Yes, this is your continuity equation for particle number. Okay, if in this equation you apply in this term the method of separation of variables, so here you apply separation of variables, so you will get one term del by del xi of udi. So if you calculate this term del by del xi of UDI, that will be equal to minus of del by del T of ND and minus of del by del xi of ND. Is this point clear? And in that term then ND you have to replace with this particular formulation eta by 1 plus eta into. You will be replacing ND with this term and then you will be again applying the derivative rule on U by V. Fine. Again you will be applying the derivative rule and then you will be getting this term as the final equation in terms of volume of each dispersed phase. Is this point clear? All are clear with this idea? So I am not deriving the mathematical term. So because that is very simple, you have to simply do some of the algebraic manipulations. Okay. And algebraic manipulation is what? First you have to apply the separation variable rule for in multiplication in the number continuity equation, and after number continuity equation you have to replace ND with this term eta by 1 plus eta V, and then you have to apply again this differentiation rule for U by V. Is this one clear? And from there you will be getting del UDI by del xi equal to eta by 1 plus eta V into dd by ddt of del V by del T. What is this ddt by ddt of V? This is again the Lagrangian derivative of volume of each dispersed phase particle. Okay. So it means the rate of change of volume of each dispersed phase particle is correlated to the yes. So if you go to the single phase formulation, then what we do? In case of single phase formulation, this term is simply called as the volumetric strain. What is volumetric strain for single phase flow problem? Divergence of velocity vector. Divergence of velocity vector is nothing but volumetric strain. So here I can say that the volumetric strain of the dispersed phase particle is nothing but equal to the Lagrangian derivative of volume of each dispersed phase particle. Okay, and with some correlation of eta by 1 plus eta. Is this one clear? So this is the step actually shown over here. Sorry, it was there actually, but I think animation was not correctly connected. So here you can see the previous step is also given. So as I told you that you have to replace eta d, and then if you do the ddt of this term, then you will be getting this term. Okay. So this is additional step is given over here. Okay. This is all about dispersed phase number continuity equation. Now sometimes we come up with a situation where actually all the phases are kind of very homogeneously intermingled with each other. Okay, and this situation particularly comes when we talk about the gaseous mixtures. Okay, so in case of gaseous mixtures, what happens? One gas is kind of completely dispersed in the entire volume. So if you consider a control volume over here, everywhere you will find nitrogen molecule, oxygen molecule, argon molecule, whatever are present in here. Okay, so in case of air or other gases, so in terms of air, actually again the analysis is not that much complicated, because whatever the component molecules are or component gases are present, these are not reacting. But on contrary, if you consider the reacting gas mixtures, there you will be finding that you will be having strong reactions also in between the molecules. Okay, so here this Fick's law also essential along with the continuity equation in order to determine the transport of properties between the individual phases. Okay, however I have given you this for the sake of completeness, but in this particular course we will not be using this, because our majority of the discussion will be beyond the reacting gaseous mixtures. Okay, so that's why for the sake of completeness I have included it. but otherwise we will not be discussing this in detail. Okay. Okay, now comes another important equation, which is even more complicated than the continuity equation. What is that equation? Momentum equation. Okay. So before going through this equation, first you have to tell me about the momentum equation for a single phase situation. So can you tell me how momentum equation for a single phase situation looks like?
Transient term.
Transient term. So let me write del by del T of rho into V vector, if I write in the vector notation, plus okay, that is equal to sum of all forces, and that is equal to nothing but gradient of pressure plus Laplacian term. Okay, Laplacian is applicable for a Newtonian fluid. Okay, if you write in more generic sense, then it will be sigma stress term. Particularly, let me write over here, okay, stress term sigma. Okay, and these stresses are only because of the viscous effect, because normal pressure you have already taken outside. Okay, and then along with this I will be having one more force, which is body force. Okay, so this is the momentum equation for a single phase flow situation. So in this you can see first term is nothing but local rate of change of momentum within the control volume. Okay, and what about second term? Convective term, and this is equal to net rate of forces acting on the control volume. Okay, so now how we can write the commensurate equation for multiphase flow problem? Okay, so for multiphase flow problem you can see with del by del T term I am having rho n into alpha n into u n k. Okay, so this is rho into v vector. So rho is individual phase density rho n, u n k is velocity of the particular phase in kth direction, and then alpha n is nothing but the corresponding volume fraction. Okay, because within the entire control volume single fluid is not present, only alpha n fraction of nth phase is present. So that's why this is the commensurate temporal term. All are clear with this term? Anyone is having any confusion? Then second term, this is again, this term I can also write it like this, del by del xi of rho into ui ui. I can write this term like this as well. Okay, in the tensor notation. So if you see in tensor notation, the equivalence is del by del xi. In place of rho now it will be rho n, and of course because only alpha n fraction we are referring to, so that's why multiplied with alpha n, and then u n I and u n k. Now what is the difference between u n I and u n k? Can you tell me? The difference is I am writing this momentum equation in kth direction. Okay, and mass I am considering normal to the kth phase. So what will be? Because whenever you calculate momentum in your control volume, say this is my control volume. Okay, this is the control volume. So in this control volume, say this is direction I, this is direction j, and this is direction k. So if you write momentum equation at this particular phase in vertical direction, then what will be happening? You have to consider the mass entering through this phase, entering through the normal boundary, So that's why to account for mass, I am having this term rho n alpha n into u n I. This is the mass flux, and this mass flux, it is having velocity u and k in the kth direction, which will be representing its momentum at that particular boundary. Is this point clear?
So there could be J, UJ.
Sorry, here it will be u. So when I have written this tensor notation, this is similar thing over here also, rho ui into uj, where rho ui represents the mass flux of the phase rho ui for a single phase flow problem, and uj is nothing but momentum. Okay, when uj is multiplied, it means uj represents the velocity of that particular phase in jth direction, that particular mass flux in jth direction. So that's why this is the rate of change of momentum through a direction. Okay, so that is the reason this is my mass flux, and this mass flux, whenever it is multiplied with velocity, it is becoming my rate of change of momentum. Okay, so this is local rate of change within the control volume, this is rate of change across the boundaries of the control volume. So across boundaries and within control volume will become total rate of change of momentum, and total rate of change of momentum must be equal to the all the total forces acting on nth phase in kth direction. Okay, is this point clear? All are clear with this idea? Net forces acting on nth phase in kth direction. Okay. Now this is important to determine how to find out F and K. So what I will be calling this is nothing but my individual phase momentum equation. This is my individual phase momentum equation. Okay. Now what we need to do, we need to determine the value of this F and K. So when we will be calculating the value of F and K, it should have three different contributions. One will be contribution because of the body force, weight of dispersed phase. Okay. Other will be contribution because of the surface forces which are acting at the boundary of the control volume, and third will be contribution because of the surrounding phases. Okay, so if you have one isolated phase present, so there can be some force applied by the surrounding phase on this individual dispersed phase entity. So that's why we have to consider that contribution also into account. Is this point clear? Now, if I consider my earlier definition of the control volume, as per which within the control volume I can have finite number of particles present. Okay, is this point clear? So in this definition, this was the definition when I have started deriving the continuity equation. So in this assumption you can see that if I consider this particle, so these are some of the particles which are nothing but crossing the boundary of the control volume. Okay, so when you will be writing the surface forces at this boundary, particularly because of the viscous stress, then in this much portion of the boundary there should be forces because of the viscosity of the continuous phase, and in this particular portion there should be forces because of the viscosity of the dispersed phase. Okay, so this type of segregation will actually complicate our analysis. Okay, so at this point what we want to do, we want to take one simplification. What is the simplification? We want to consider that wherever near the boundary I am having any dispersed phase present, there I will be slightly deforming the boundary so that everywhere through the boundary of the control volume I am having contact of continuous phase. Yes. Is this point clear? Because if you go without this assumption, then each and every boundary you should know what is the fraction of this boundary covered by dispersed phase, what is the fraction covered by continuous phase, and calculation of that fraction is actually very, very challenging. So that's why what assumption we are considering, that wherever I am having dispersed phase present at the boundary, it is interfering with the boundary, there I am slightly deflecting the boundary in order to include that dispersed phase completely within the control volume, so that everywhere boundary is actually in contact with the continuous phase. All are clear with this idea? So this will make our calculation of surface forces very, very easy. And now, just now I told you three contributions. One is contribution because of body force, second is near the boundary of the control volume, and third is because of the other phases. So if I take this assumption, then my contribution, second contribution, okay, like forces on the boundary of the control, forces on the dispersed phase because of the boundary of the control volume will actually vanish. Okay, this contribution will not be there. And this contribution is not causing much error, because whenever we are deforming the control volume, the deformation of the control volume is very small, because already we have assumed that my control volume should consider finite number of particles. So if it is considering the finite number of particles, it means each particle size is very small in comparison to the total size of the control volume. So that's why, because of the deformations, there is minimal change in the volume of the control volume. Okay, is this point clear? All are clear with this idea? Now, one by one, if I consider the forces, so first will be my body force. Okay, so body force, because I am writing this momentum equation in kth direction, so I will be using the component of the gravity in kth direction. So Gk, rho n is density of the nth phase and alpha n is volume fraction, because total mass of the control volume is not of same phase, but it is only having alpha n fraction of that particular phase. Okay, so this is my body force. Then when I will be considering the surface forces, I told you earlier this del of sigma, or I can say del by del xi of sigma ki. Okay, so when I will be considering the surface force, because of the assumption just now I told you, surface force at boundary of CV, at boundary of control volume, will only come because of the continuous phase. That's why I am writing this sigma as nothing but sigma C. So del by del xi into sigma C ki. Okay, and this I am writing sigma C because of the assumption just now I told you. Is this one clear? Okay, so now further we will discuss in the next class.